have Ashwin Nayak here from University of Waterloo, and Ashwin's going to talk about randomized decision tree complexity of recursive majority.
Thanks, Paul, and thanks, Ryan, for inviting me over. So this talk is about a very simple, well, seemingly simple problem in complexity theory from, in fact, about more than 25 years ago now. It's called recursive majority of three. And it's joint work with Frédéric Monniers, Miklos Shanta, and, well, that's me in the middle, and David Shaw, all of whom are at Paris. So you may actually be familiar with it. I'm sure some of you have even worked on this problem. It's the problem of evaluating a formula that's defined recursively using this majority 3 gate. So you have this gate on 3 inputs, x1, x2, x3. And of course, it evaluates to 1 if and only if at least 2 of these variables are assigned the value 1. You can construct a formula using this one gate over 3 to the h variables, which you can imagine are arranged as the leaves of a complete ternary tree. And then at each of the internal nodes, you have this basic gate, the majority 3 gate, right? Oops, sorry. So you have this complete ternary tree, at the leaves of which you have the variables x1, x2, all the way up to x sub 3 to the h. And then at each internal node, you have a majority of 3 gate. So a simple recursive generalization of majority of 3. The question we are interested in asking is, given an assignment to this to these 3 to the h variables in the form of a black box, how many of these variables do you need to evaluate or to query in order to determine the value at the root? Right? So there's a natural way in which the function is determined by the gates in the internal nodes, and the question is the problem is to evaluate the value, evaluate the formula that's the value at the root. And this measure of the number of variables that you need to query is, well, in the case of deterministic algorithms or deterministic procedures, the deterministic decision tree complexity of the problem. In the case of, well, if you're only concerned with deterministic algorithms, then it's not very difficult to see that you need to indeed query all the variables. Okay, and I'll maybe say a little bit about this in a bit. So you can imagine the hardest kind of inputs for the problem are of the following sort. So at each gate, imagine having evaluated the value of the 3 children. Then the hardest instance in the hardest instances, basically what you would have is that 2 of these gates would evaluate to the same value, and 1 of them would be different, right? And you can propagate this sort of a threshold kind of instance all the way down from the root to the leaves, right? So you set the value of the root to 0 or 1, and then you can pick any one of the 3 children to be basically the minority child of the root, and then assign it a value different from the root, assign the other 2 subformulae values equal to the root, and then recursively construct your instance that way, right? So these instances I'll label as hard instances. So as I said, for h equals 1, it basically looks like 0 or 1. So let's say a value b, and then one of its children gets value b bar, and the other 2 get value b. Right? And there are 3 such settings of these 3 subformulae. And you recurse this construction for general h. Okay, so in each of these hard instances, what you can immediately see is that a certificate for whether the formula evaluates to 0 or 1 consists of 2 to the h values, or 2 to the h variables, and their corresponding values, right? So if you want to be sure that the root evaluates, let's say, to 0, then you must know that 2 of its children evaluate also to 0. And then 2 of the the grandchildren of each of these children must evaluate also to 0, and so on, right? So a certificate of these, in these hard instances is of length 2 to the h. And another thing that you might notice is that if you take any path along from the root to the leaf along one of these certificate nodes, and you flip the value all the way, of the leaf, of the bottommost leaf, then this basically flips the value of the formula, right? So for instance, here if I flip one of these b's to b bar, then the value of the parent also flips, right? So just using this observation, you can argue, it's not a difficult argument, that any deterministic algorithm for this problem will have to examine all 3 to the h variables. And I'm not sure, but there may well be a more generic argument for Reed-Wadson's formulae of this kind that says that the deterministic complexity must be n. Okay, so a very early observation, probably due to Boppner, was that this naive algorithm can be defeated by a very simple recursive randomized algorithm. What's the randomized algorithm? Well, if you want to evaluate the root, what you do is you pick a random child of it. Let's call it y1. And then you don't just pick one, you pick 2 random children. So let's say y1 and y2. You evaluate y1 and y2. If they're equal, clearly you have the value at the root. And if they're not equal, you evaluate the third one. And again, you're done. The value at the root is necessarily the third one, right? So these 2 are different, and y3 has to be equal to one of these 2, and then that would be the majority, right? So if you look at just this height 1 tree, you can calculate the complexity, the randomized complexity of this simple algorithm, and what you get is the complexity of this formula of height 1 equals Well, you always evaluate y1 and y2, so you get a query complexity of 2, and then if you have a hard instance at this point, so an instance of this sort, the probability that y3 is actually the minority is simply 1/3, right? So with probability 2/3, right, you will end up in the situation where y1 or y2 is the minority, in which case you will necessarily evaluate y3, and so you would have an expected query complexity of 8/3. Right, so this is the expected number of queries for a height 1 tree. And you can generalize this to height h in the natural manner.
So this is for the distribution of hard instances, for a random hard instance?
No, in fact, this is the worst case complexity, expected. So
why is 2 sort and not 1/2?
I'm sorry?
Why is it 2 sorts and not 1/2? Can you repeat briefly? Because I guess I missed it.
Oh, okay.
It's only one.
Okay, sure.
Yeah, so if all three are equal, then the complexity would be 2. And the harder instance is when at least one of them is different from the other two, right? And in which case the complexity, the expected query complexity would be 8/3. So this generalizes in the natural manner to height h formulae. And of course, what you do is simply imagine these, in fact, to be subtrees of height h minus 1. In which case, what happens is that for the same reason, for the same kind of hard instances, you would have query complexity, well, 2 times t of h minus 1, because you evaluate 2 subtrees entirely, and these 2 subtrees are of height h minus 1. And then again, it would happen with probability 1/3 that the one that you left out was the minority. And a better way, a less confusing way of saying that is the chance that the minority is not, or rather is in one of y1 or y2 is actually 2/3, right? It's equally distributed, or rather, because I have permuted these 3 children, the probability that it happens to be one of y1 or y2 is 2/3, in which case you would have to evaluate the third one as well. And of course, if you have a height 0 tree, so just one variable, to evaluate its value, you have to make one query. So you get t of h equals 8/3 to the h. Yeah?
It's clear that so the problem of checking if y1 equals y2 seems to be slightly easier, not necessarily as hard as evaluating both of them. Or is it?
That's a good point. It's an easier problem, yes. You have to evaluate the parity, right? And I'm glad you asked this question because not in the, okay, so the problem in the classical case is open, but I can tell you that if you wanted to consider the quantum case, quantum algorithms, you can speed up that first step where you have to just evaluate whether y1 equals y2, right? So you can basically check if y1 equals y2 with one quantum query. mention. So there is a lower bound of 2 to the h, and maybe that's all I want to say about it at this time, because it would be a digression.
Yeah, that's what
Right. Oh yeah, you would know that.
yeah, but I didn't know for this one. That's why I was asking.
Okay. Okay, so for a long time, it was not known how far this naive recursive algorithm was optimal. In fact, there's an observation, or at least, well, I think Michael Sachs and Avi have mentioned in an article on a related problem, which is about the recursive NAND tree, that this naive algorithm is not optimal.
For majority.
For recursive majority, yeah.
So they knew it was not optimal.
That's right, yeah, but they didn't quite give an explicit algorithm for the problem. I guess it's not too difficult, but the explicit algorithm that I know came much later by Jayram, Sivakumar, and Ravi Kumar. So they gave an explicit algorithm which achieved complexity that was slightly smaller than this. So this is something like 2.666 to the h. The explicit algorithm that they gave came to 2.656 to the h. Okay, so this particular number is not really illuminating. What is more illuminating is the algorithm that they give, and I'll get into that in a bit. On the other hand, not very many. There weren't very many results known about the lower bound side at all. So I guess there was this lower bound due to Hyman, Newman, and Wigderson from 90, which said that any threshold formula of depth d, so something of this sort, recursive majority of 3,
And read once.
read once, that's right, has complexity, which is so randomized two-sided error complexity is at least omega n divided by 2 to the d. And then result, let's see, is it Hyman or Newman and Wigderson? I think Hyman. Soon after gave a slightly stronger lower bound for general read once formulae, which said the randomized complexity is at least the deterministic complexity raised to power 0.51. Okay, so slightly larger than 1.73 to the h for recursive majority of 3. And then there was a complete roadblock until the work of Jayram, Kumar, and Sivakumar, and this is from 2003, where they came up with a very elegant lower bound method that gave a lower bound that came quite close to this. And went something like 7/3 to the h. So this is 2.333 to the h. Right?
Regarding earlier too, isn't it obvious that 2 to the h should be a lower?
Okay, so in the rest of the talk, I'll show you some improvements to these bounds that Jayram, Kumar, and Sivakumar came up with, and both of these bounds are obtained by strengthening the method that they developed back in 2003. So what I'll do is I'll state the improvements, and then go into a little bit of detail into how they derive these lower bounds and the upper bound. And I'll in fact start with the upper bound, and hopefully I'll be able to sketch all the arguments in sufficient detail. Okay, so what we're able to show is that first you can improve the lower bound from 2.33 to the h to 1 minus 2 delta times 5 halves to the h. So this is like 2.5 to the h. Okay, and the upper bound itself you can improve to something like 2.649 to the h. Okay, so again, these numbers are not really what is significant here. I guess as you'll see the details of this argument, what will become apparent is that there are a few principles at work behind both the algorithm here and the lower bound that they showed that haven't been exploited to their fullest. And it looks like what we've done is basically inched forward in pushing these methods further, but then we haven't quite arrived at what would really help us characterize the complexity of this problem. Okay, so one of the biggest lessons that we at least have learned so far by looking at this problem is that unlike the quantum case and unlike this naive recursive algorithm, which happens also to work for a few other recursively defined formulae, recursive majority of 3 probably does not have a simple recursive optimal algorithm. Okay, so it has, as you'll see, a hierarchical algorithm which has some recursive structure, but it's neither easy to state or simple to state, or nor simple to analyze, at least as far as we know. Okay, so let me start with the algorithm. And maybe what I'll do is I'll start with the algorithm that they presented, which I guess which has its roots in this naive algorithm. And what it does is it tries to refine this idea that you evaluate children or evaluate nodes of the formula only on only if you really need to. So here the idea was that you would try to avoid the minority child of the root, and so you would pick, well, 2, not all 3, but 2 of the children and evaluate them, and hopefully you would have evaded the minority, but of course you can't do this for sure, so with some tiny probability you would eventually also have to evaluate the third node. So the JKS algorithm takes this a bit further as follows. So let's look at, so it's easiest to understand if you look at a height 2 formula. So you have a tree on 9 nodes. So what they do is they even try to avoid having to evaluate the first 2 nodes entirely. So what they start with, well, they start with evaluating one node. So they pick a node at random. Let's say it's y1. And then instead of evaluating a second node completely, they actually test to see if they should or not, right? So they pick one of the 6 grandchildren other than those in y1 at random. So let's say you pick this one here, x2. You evaluate this node. And now this node gives you an indication of what the value here might be, right? So if these two are equal, you then complete the evaluation of y2 here. And if not, you go to y3, evaluate it completely. So of course, it might happen that when you evaluate y3, it turns out not to be equal to y1, in which case you do need to evaluate y2, and you come back here, right? So let me just summarize this in an actual decision tree form. So let's say what I do first is I permute y1, y2, or let's imagine that y1, y2, y3 are a random permutation of the 3 children of the root. You evaluate y1, and then you evaluate a random child of y2. So here, this is a random, let's say, niece. And there are 2 cases. If x2 happens to be equal to y1, this is a good indicator that y2 might be equal to y1, and we should evaluate it. But of course, there is a chance that it might not. If it is, you have your answer. If not, then you have to go on and evaluate y3.
So if you found the second one, second child of y2, and you get equality there, then you don't finish evaluating y2? Like,
That's a good point. I was going to expand this bubble out here in a moment. So you don't do it in a, you do it in a parsimonious manner as you suggest. So again, this is like imagine this is a height 1 tree, and that you evaluated one child of it. So you pick a random child from the other 2, evaluate that, and then follow the same kind of idea as we had in the height 1 case. If they're equal, you're done. If they're not, then you evaluate the third child, right? So all of these little bubbles here, I'm sure, are giving you some idea of the logic at work, right? Maybe, let's see. I'll just write down one more branch of this and keep it around. I'm glad I'm running out of space because I'm sure you can complete, well, one, I don't need to write it. You would be able to complete it based on a similar kind of logic. The other side is probably more interesting. So here you evaluate y3. If they are equal, you're done. That's the uninteresting case. And if not, you have to come back to y2. Right, and again you're done.
So the question I was asking is, after you've decided, based on x2, I'm going to evaluate y2, if the valuation of y2 starts to look iffy,
No, you do complete it.
you do complete it.
That's right. So let me just write it down. So this is like you pick so you pick at random from the remaining children of y2. Then you evaluate x2 prime. There are two cases, x2 prime equals x2, and you're done. If not, you evaluate the third child. And again, there are two cases. I mean, at this point, you know the value of y2. It may be equal to y1 or it may not, right? So again, there are two cases.
So Ashwin,
Yeah,
so what's going on is that you are sort of doing this look ahead up to some constant number of levels, right?
that's right.
So presumably you could code this up as an integer programming package and get the best possible algorithm you can get. Right?
That's right, yeah. It should be. I don't think so, no.
Or is it
Yeah, it's possible.
No, I mean, yeah, depth 2 or depth 3 or whatever, right? And get the best algorithm, the best constant you can get.
Right, I think one of us has, we did it by hand, in fact.
Yeah,
I mean,
yeah,
the
yeah.
depth 2 thing was doable by hand. And so this is not the optimal depth 2 recursive algorithm. So that's for sure. And in fact, the upper bound that I'll present will be an improved depth 2 recursive algorithm.
So you don't even know how to do depth 3, say, for example.
That's right. So we have the principles in place, but possibly if we coded it up and did a search, it might.
Executing it is challenging.
I'm sorry?
Executing this, implementing these principles is challenging.
Yeah, analyzing them. Yeah, I mean, implementing them is easy.
As an integer program should not be.
Yeah, you can write down, you can automate it, but coming up with a bound seems to be the harder part. Okay. So instead of actually showing you an analysis or why this is better, maybe I'll just point out how you can improve it. What are the elements that go into analyzing this new algorithm, and why we can't? I mean, at least I don't see a way of doing it for depth 3, analytically. So we may be able to automate this process of finding the best depth 3 recursive algorithm, but analyzing it, at least at the moment, seems pretty difficult. Okay, so what is the improvement? It's based on this principle that you can gauge the value of a node of this formula by looking at one of its descendants, right? And in these algorithms, what we've been doing is looking at basically a grandchild to get an opinion about the value of one of the children. And so this is exactly what we do for not only y1, but sorry, y2, but also y1. So you start instead of evaluating a child entirely, you form an opinion about the value of this child by looking at one of the grandchildren. So maybe I'll just write down the principles. So form an opinion on y1 by evaluating a random child of y1. Same for y2. If the opinions are the same, you start by completing the evaluation of one of them. So let's say you completely evaluate y1, and you do this, again parsimoniously. So you would follow the same kind of an algorithm as we had here. Right? And okay, at this point, you might get a value for y1 which is different from your opinion, right? So in that case, you get back into the situation right here in the JKS algorithm, where you have the value for a child, you have the value for a random niece, but these two values are different, right? So you complete the evaluation of the formula in the same manner as in this branch. And in the happy case, when the opinion of y1 equaled its value, the one that you got by completing this evaluation, then you would continue with evaluating y2, right? And so on. So you can imagine how the rest of it is completed. It's very much based on the same idea that instead of evaluating a child, you go to a grandchild first. Okay. So maybe I'll point out a few things that come into the analysis of this algorithm. One is, it looks like the simplest way to analyze a recursion of this sort is to one, condition on the relative values of first the children and then the grandchildren. So we generate recurrences by conditioning on relative values of y1, y2, y3. The second thing that simplifies the problem is to basically use these recurrences to show that the hardest instances for this kind of an algorithm is precisely the kind that I generated in the beginning, right? The ones that I constructed. The third thing that happens is that we take care in analyzing the evaluation of a subtree of this form where we are interested in the value at the root here, but we've already partially evaluated one of its children. Well, we've partially evaluated the tree by evaluating one of its children, right? And here it makes a big difference to the complexity whether you were lucky in that x2 was one of the majority children of y2 or whether it was the minority. So you have to distinguish between those two cases, and so you get 3 recurrences. So you get simultaneous recurrences between the complexity of the entire algorithm, then the complexity of this piece where we are completing the evaluation of a partially evaluated tree. And there are 2 cases for this, when the child is a minority and when the child is actually a majority child. Okay, so once you do this, you're left with this problem of solving a set of simultaneous recurrences in 3 quantities. And of course, this only would get only worse if you go into deeper recursions. And here, the way we analyze this is by forming an educated guess on what the solutions would be, and basically proving it by induction. And there's a numerical way of doing it as well. You can sort of refine your guesses based on initial guesses and so on in a natural fashion. Okay, so I don't know of a simpler method of solving such recurrences either. All right, so maybe that's all I'll say about the upper bound. In the remaining time, sorry.
So you said, so if you know you have one of the hard instances,
Right.
do you have a better algorithm for this limited case?
No, I mean the simple answer is no. It turns out that well, our intuition is that the hard instances are precisely the hardest instances, right? So if you would get a better algorithm for those, you would get a better algorithm for all instances.
I guess
right?
the
And
question is maybe can you use the specific structure of the hard instance somewhere to bear on that, or is it true that any algorithm or any recursive algorithm of this kind, if it does well in the hard instances, it does well overall?
that's actually open. We were not able to show that an algorithm. So so just showing that of course showing that a particular distribution is the hardest distribution is equivalent to finding the optimal algorithm. So we were not even attempting that. But even showing something like this algorithm, for this algorithm, the hardest distribution is the one on those hard instances is not straightforward, right? So even that is open. So the only way we saw of proving that is by first coming up with these recurrences and then showing that basically it followed from the recurrences directly. Okay, so it's once you start getting your hands dirty with this problem, you see that it's not as straightforward. Even for a given algorithm to show that the hardest distribution is the one that we expect. Okay. All right, so in the remaining time, what I'll concentrate, I'll shift gears and go into the lower bound that we show. So this lower bound is basically a refinement of the Jayram, Kumar, Sivakumar lower bound technique, and it's a beautiful technique. And what it does is that it relates the complexity of recursive majority of three of height h to a quantity that is related to this hard distribution that we've seen over and over again. So let me make a few things precise. So let me denote by this script h sub h to be the uniform distribution on the hard instances of height h. So for each of these, for each of the points or each of the inputs in this hard distribution, we can define a path from the root to the leaf, which we call the minority path. Let's denote it by m sub x, where x is a sample point. So I'm going to use h sub h for both the uniform distribution on these hard instances and for the sample space itself. So let's say x is one of these hard instances. This minority path consists of the unique root to leaf path in x that follows the minority child at every node. Right, so just to give you a very quick instance, let's say the instance is such that the root evaluates to 1, and then its children evaluate to 1, 0, 1, and finally you have 1, 1, 0, 0, 1, 0, and then 0, 1, 1. So the minority path for this instance is the one that starts at 1, goes to 0. Oh, okay, that's that simple, right? The leaf at the end of this minority path I shall denote by little m of x. And then I shall give another name to nodes in the middle. So node in the middle at depth, let's say d, I shall denote by m of x sub d. So this is the dth node in the root leaf path. Okay, so something to note is that mx0 is the root, right? Simple observation. So if you'd like to look at the number of queries that any algorithm makes, then it suffices to look at how many queries the algorithm makes to variables that are descendants of the root, right? That's just the definition. But we're going to extend this definition to all the internal nodes that also lie on M of x, right? So we are going to, so let me introduce some more notation. So let's say for a node V in the ternary tree. So every instance I view as a ternary tree. So in the ternary tree X, Z sub V is the set of leaves in the subtree rooted at V. Okay, so we're going to look at not only the variables under the root that are queried, but we're going to refine this a bit further. We're going to say, we're going to look at the variables under the dth minority node in M of x that are queried.
So does he require that they be queried?
Oh, no, sorry. So these are the variables that are that we'll be looking at. So let me define these quantities now. So consider an x that has been drawn from this distribution over hard instances. Right? We'll look at this quantity. I'm going to call it I because there is an information theoretic interpretation of it. So this is a quantity that depends on the height of the formula that we're going to evaluate, and also this parameter d, which will relate to basically the depth from the root that we're going to consider. So this is the expectation over the hard distribution. So we've picked an instance from this distribution of the number of nodes in Z of or Z of M of x d that are queried by an algorithm, let's say A, and we are actually going to minimize over all such algorithms A. So we're going to minimize over algorithms. So we're going to look at the best algorithm with error delta that makes best algorithm as in the one with the least expected query complexity. And we're going to look at the nodes under this one that are queried. Okay. Oops. So JK has showed a beautiful recurrence between these I quantities. They showed that I of HD is bigger than equal to I of HD plus 1 plus 2 times I of H minus 1 D. Okay, and this is for H bigger than equal to 1. Okay, so maybe a few words are in order explaining how this comes about. let me use this diagram out here. And let's just work with the root, right? So we are interested in how many variables under the root that are queried. So clearly, the variables that are queried either lie in the first subtree, the second subtree, or the third subtree, right? So this expectation is basically a sum of expectations of three quantities. Now, each of these three quantities is basically, because of the symmetry in the hard distribution, is the same, right? So now you need to only worry about two things. One is what happens when under this hard distribution, let's say this particular node is a minority child versus a majority child. When it's a minority child, what's happening is that the quantity in which you're interested is basically looking at the d plus 1th, so the node in the minority path that is one lower than the one that you were considering. So the d plus 1th minority child in the minority path, and then you're looking at the number of descendants of that are queried. So this is how the first term in this recurrence arises. And the second term in the recurrence arises by noticing what happens when this node is actually a majority child. In that case, basically, what you can imagine is that you use this algorithm that you are trying to analyze, the optimal one, to solve not just recursive majority of h, but recursive majority of h minus 1 by basically planting it out here, okay? And then giving these two nodes value 0 and 1, and then completing them in the manner the hard instances are constructed, okay? And then it's a somewhat technical argument, but intuitively not too difficult to see, that this is precisely the number of queries an algorithm makes in evaluating a formula of height h minus 1 under a minority child at depth d. Okay, so that's how this recurrence arises. All right. I guess I'm running out of time, but sorry? What's the protocol?
About 12.
Okay, thanks. That gives me a little bit more time. Okay, so this recurrence is not very difficult to solve. If you actually see it through, what you get is that the quantity in which we are interested, which is the number of queries that you make under the root for a depth height h tree, is at least the summation I going from 0 to h of h choose I 2 to the h minus I times, let's write this as, this is not a very prudent choice of variables, but anyway, capital I of II. Okay, so what is this quantity? This quantity let me use J here. This is the minimum. Okay, so this is, let's just write it as, let's fix our algorithm A, right? So this is exactly the probability that algorithm A queries the absolute minority, so the minority leaf m sub x when x is chosen from the hard distribution for height j instances of the problem. That's right, optimize over the best algorithm A, right? So if you think about this quantity, so here's what happens. I mean, think about any algorithm that solves the problem. It has to look at least one of the variables. It has to query at least one variable. If it does not query any variable, then under the hard distribution, the value at the root is equally probable to be 0 or 1, so it will make error 1/2, right? And so if the error is bounded by delta, then with probability at least 1 minus 2 delta, at least one variable is queried. Okay, and let's say it's x1. It doesn't matter. It's I mean, the whole thing is symmetric under the hard distribution. The probability that this one variable, the one that is queried first, is the absolute minority is at least 1/3 to the h, because of the way the hard distribution is defined. So the probability that x1 is exactly 1/3. In fact, in this case, it's 1/3 to the j. And this implies that I of h, if you just plug that back in there, you get I of h0 is, maybe I'll use a different board. So this becomes bigger than or equal to one minus 2 delta times summation I bigger than or equal to 0, h choose I, 2 to the h minus I, 1/3 to the I, and of course this is 2 plus 1/3 to the h. Okay, so when you look at this argument, you can't but help wonder if this was the best you could do, right? And that's exactly what we did, and we stared hard at this and realized already that, well, if you look at small instances, it's very clear that 1/3 to the j is not the optimal quantity out here, right? So you can look at depth, optimal algorithms for depth 1, depth 2, and so on, and you see that immediately, I mean, even just looking at, you know, the initial sort of numbers, capital I, little I in the sequence, you can improve the lower bound slightly, right? So, so the question we asked was, what is the least this quantity could be? So given an algorithm that solves the problem with error delta, could we show a bigger lower bound on the probability that the absolute minority is queried? And we showed, indeed, you could show that this quantity is at least 1 minus 2 delta times 1/2 to the j, which would give you I h0 at least 1 minus 2 delta. So 2 plus 1/2 to the h, so this is 5/2 to the h. Okay, and maybe a few final words on how how this is obtained. So imagine a height h formula. And an algorithm A for it. We show that from this algorithm for a height h formula, you can derive an algorithm for height h minus 1 formulae such that the probability that A queries the absolute minimum for height h is at least 1/2 the probability that A prime queries the absolute minimum for h minus 1. Okay, and at the tail of this, at the end of this recurrence, you basically have that for a height 0 formula, you need to query that one variable with probability 1 minus 2 delta, and so you would get 1/2 to the h out here. Okay, so how do you get this algorithm A prime? It's quite different from the one that I very quickly mentioned in the derivation of this recurrence. What we do is we take a height h minus 1 instance, so that would come up to this depth, and then we extend it into a height h instance. Okay, and the way we extend it is slight. Well, it should be, you know, it needs a little bit of care in order to show this recurrence, and the best way to do it is the following. You know that you have to somehow evaluate. Well, you have to construct an instance here such that the value of the formula would be the same as the value of the formula on the h minus 1 instance. So you create these 3 values here so that y is the majority of these 3, right? So you assign a random one of these 0, a random one of these 1, and then the other one is assigned y. Now which one is assigned y is carefully chosen, and it's chosen so that this argument basically becomes, it simplifies this argument, okay? So the idea is, maybe instead of showing you the details, is basically that when the algorithm A queries some variable here, tries to query a variable here, either we know the value that we've given to it by this extension, or we need to query y. Okay. Now, this algorithm basically thinks it has a height h formula, right? And for it, the minority is the one among 0 or 1 that's different from y. Okay? So every time, well, what we show is that every time this algorithm A queries some variable here, there is some chance that A prime will query the same variable, and that will be the absolute minimum for y, right? So for the smaller instance. Okay, so there's basically a mapping between the sample space here and the sample space here, which makes a bijection such that this recurrence follows. Okay, so maybe that's as much as I should say about that. Again, when you look at this refinement of the argument, it should be it should be clear that it's not really the best you could do. You could imagine trying to do a better embedding. In fact, or rather showing a stronger recurrence of this form, let's say by going to depth h minus 2 instances, right? And the problem that occurs out there is in trying to get an embedding that, of course, helps you get a stronger recurrence like this, but then also in trying to minimize this quantity over all possible algorithms a prime, right? And the particular difficulty here is not just that you're worried about algorithms that compute recursive majority, but when you restrict to particular subtrees out here, the restriction of the algorithm is no longer a decision tree for the smaller instance at the bottom. Okay, so it can be an arbitrary decision tree on the number of 2 to the j variables if you're considering this slice of width j. And that becomes pretty hairy already if you try to do it by hand, whereas this depth 1 embedding was not that difficult. Okay, so I think it's time to stop. Thank you very much.